that with one way in between, it would have been good to go to some of the theory again. So we're currently doing, and the you cannot be an expert in all these fields, at least I cannot. So what I do is to rely a lot on collaborations, mainly industrial collaborations that are helping us in all these fields. So I'll be showing you some of the things that we have been doing in the simulation of gas-liquid bioreactors. We are particularly interested in bubble columns working under the homogeneous and heterogeneous regimes. Then I'll show you some of the recent work that we are doing in the field of boiling flows, liquid-liquid dispersions. Then there are a number of other applications that I will not talk about for the sake of time, soot formation in flame, complex fluid in porous media, and simulation of precipitation and crystallization of solid particles. As you can see, all these applications have something to do with energy production and energy storage, which is the theme of this workshop. Something else I want to mention is that the interaction with all these industrial and academic collaborators is very interesting because they are providing us with challenges, ideas, but especially with industrial collaborators, we often are very practical and empirical solutions to the problems that we are trying to address. So some of the fundamental work is done with money coming from the European Commission, and following up on the discussion we had yesterday, I can, if you want, some of the ideas currently discussed at the European Commission level in order to find ways to fund research projects in fluid mechanics. All right, so what we do, as was explained by Rodney on Monday, is to basically look at multiphase systems through distribution by looking at this governing equation, this master kinetic equation. And the distributions we look at are bubble or droplet size distribution in our case. And instead of solving this equation directly, what we do is to look at the moments of this distribution. So in this case, the moments are just function of time and space. Therefore, the governing equation can be solved within CFD with finite volume discrete. That you end up with a closure problem, and the closure problem is related to movement of the elements of the dispersed phase in the physical space, but also is related to the rate with which these elements of the dispersed phase, mainly bubbles in the presentation, coalesce. So one way to overcome this closure problem, which is a mathematical closure, is to use a quadrature approximation, because the closure problem is at the end an integral, and one efficient way to solve an integral, to calculate an integral, is to use a Gaussian quadrature approximation. So the idea is very simple. It was developed in the late 90s by McGraw. It is called, the method is called, take a set of moments of these unknown distributions, and we use these moments to calculate the quadrature approximation, know the weights of this quadrature approximation. This is basically equivalent to assuming that this population of bubbles and droplets is constituted by some small, medium, and large bubbles, and this is equivalent to assuming that the underlying distribution, which is unknown to us, is constituted by a summation of Dirac delta functions. This is nice, working very well. However, when you are looking into multidimensional problems, for example, we are very often interested in bubbles and droplets, in which we have a component moving from the dispersed to the continuous phase, and you also have chemical reactions involved. In these cases, bubbles and droplets are not only distributed over their size, but also they are distributed over their concentration. So in this case, you need to have a multivariate, a bivariate, in this case, quadrature. And to do that, you need to use another method, which is based on the idea of conditional moments. It is called conditional QMOM. In some other cases, you might want to replace these Dirac delta functions and these representation of the number density function of the distribution in terms of continuous function. The extension of this methodology to generic kernel functions was done by Rodney and these collaborators in Paris, and is called extended QMOM. And some of the results I'll show you today have been obtained by running simulations with QMOM, CQMOM, and DQMOM. And I will also try to give you a feeling of what are the issues that you encounter when you try to implement these methods into CFD codes, mainly using commercial codes such as ASCII Fluent and open source codes such as OpenFOAM. All right, so very quickly, what are the main issues you encounter? Some of these are numerical issues, some other are instead issues related to the treatment of the disperse phase velocity. So as far as the disperse phase velocity is concerned, what we typically do is to either assume that all the bubbles, all the droplets are moving with the same velocity, which you can calculate with algebraic models or differential models by using the mean size of these particles, of these droplets or bubbles. In some cases this works, but in some others it doesn't. So you have to assume that bubbles and droplets of different sizes will move with different velocities. So to do that, you can assume that there is instantaneous equilibrium between the bubbles, the disperse phase elements, and the surrounding continuous phase. And you can, for example, assume that there is a relationship between bubble or droplet velocity and bubble or droplet size. And you can assume, for example, that this relationship is a polynomial. If you do that and you plug these velocity polynomial approximation into the moment equations, you end up with a closed set of equations, because the unknown coefficients can be calculated as a function of the known moments. And there are then other ways to treat that, and some of them have been discussed by Rodney on Monday, but the results I'll show you today have been obtained by using these two approaches. What we are trying to do, especially when it comes to the application of these methods in OpenFOAM, is slightly different from what other people are doing. We are trying basically to develop libraries that we can attach not to one single specific solver in OpenFOAM, but that can be transferred from one solver to another. And so in this paper, which we submitted to the Computer Physics Communication Journal, we are showing how that is done. And if the paper is going to be accepted, as you know, attached to the journal, there is a repository from which you can load the solvers, and here I'm just showing an animation in which this velocity polynomial approximation is used to simulate segregation by size moving in a stack. Probably can be a bit quick on that. It was extensively discussed by Rodney. The main problem is that moments are not just random numbers. You need to have an typically solve the equations for some moments of the size distribution. You need to use numerical methods that preserve the relationships, the constraints that the moments have to respect. So the most intuitive is variance, the relationship between M2, M1, and M0, because the variance of the distribution is positive. So when you are using, for example, first order upwind spatial discretization scheme, everything is fine. As soon as you move to higher order schemes, what can happen is that you can, from time step to time step, break some of these rules and some of these constraints. And so that is basically leading to a disaster. So there are mainly two solutions to address this problem. When you're using commercial codes, there is really very little control that you have over the way in which the equations are solved and integrated. So in this case, the strategy we are using is basically a brute force method in which we implement algorithms that are capable of telling you whether a set of moments is realizable or unrealizable. And if it is unrealizable, the algorithm is also capable of changing one of the moments in order to take an unrealizable moment set and transforming it into a realizable moment set. Of course, if you are using instead an in-house code that you wrote yourself or an open source code in which you can instead play a lot with the way in which the equations are integrated, then you can do something better. You can, for example, follow the instructions of this paper that shows you how you can implement a numerical scheme that preserves reliability. Because of the reason I mentioned before, because we are trying to develop this library which is compatible with different solvers, what we are trying to do is to use numerical schemes that are also the very same schemes that are used in other parts of the code. And so what we do is to use, for example, flux limiters also for the moments, and we have developed a way to do that, preserving not only reliability but also boundedness. So in this paper that we are submitting to Journal of Computational Physics, we are showing how that works for a simple pure advection Riemann problem. And we have the classical analytical solution, and basically the method is capable of having high accuracy and also avoid oscillations. We are worried about oscillations because the moment of order 3, for example, with respect to bubble size is related to volume fraction, and volume fraction has to be bounded between 0 and 1, of course, and you want also the moment of order 3 to be bounded in the same way. All right, so that's enough for the theory. Let's go through some of the applications. The idea is to go together through these applications and find and discuss what are the possible challenges to simulate real industrial processes. So the first example is gas-liquid bioreactors. We heard it on Monday and Tuesday. When you want to simulate gas-liquid systems, but also other multiphase systems, of course, you need to include all the interfacial forces, and drag is one of the most important forces. We have correlations telling us what a gas air bubble is doing in pure water, in contaminated water, but these are correlations valid only for isolated bubbles. If you have bubbles in a bubble column, then you have the interactions between the different bubbles, and that usually is accounted for through correction factors that account for this swarm effect. There are many correction factors available. We are using, for example, this Simonet correction factor, which is completely empirical. And to give you an idea of how important that is, these are experiments and simulations that we have run together with IFP Energy Nouvelle. This is the global gas holdup in a bubble column versus the superficial velocity. These are the experimental data. This is the prediction you get by using the drag force correlation for the isolated bubble. That is, as you can see, is completely wrong, whereas this is what you can get with this correction. Now, which is, of course, much better. There are two things I should say here. The first one is that by using such an approach, you can switch from homogeneous to heterogeneous regimes in a continuous way, also describing what is happening at the transition between the two. But of course, this correction is fully empirical. So there is no theoretical basis. There are numbers in the correlations which work for this case. By the way, we had in this case to pay a trick on the trick because the correction has to be corrected further in order to have that. So clearly, this is not fully predictive, right? So I think as a community, one of the things we need to do is to look at some of these correlations and come up with better correlations by using, for example, the multi-scale strategy that was discussed yesterday and the days before. Another important problem we are dealing with is the effect of additives. So again, to give you an idea of how important that is, this is again global gas holdup in a bubble column versus the superficial velocity. And these are measurements performed with demineralized water, tap water, and with a bit of alcohol. As you can see, the impact is tremendous, is incredibly large. The additives impact not only the gas holdup, but also the bubble size. So we also need to come up with good correlations to address these issues. For example, for coalescence and breakage, because clearly the effect of these additives is affecting the way in which bubbles are coalescing and breaking. So for coalescence and breakage, what you can do, there are different models, which we call kernel, that can describe the way in which bubbles break and coalesce. There are many different mechanisms involved. In this presentation, I'll mainly talk about turbulent fluctuations. And for breakup, for example, there is one very famous kernel developed in the 70s by Kolaluglu and Tavlarides. This was one of the first ones. It is extremely robust. People are using it, but there is only a very limited number of phenomena accounted for in this kernel. So if you have, for example, a disperse phase, which has a high viscosity, this is not the kernel you're supposed to use. And also, this kernel is not accounting for the presence of additives if it is not for the interfacial tension. Also, you have parameters in these kernels that you need to fit from one system to another. They might change. So this is also another issue. Concerning coalescence, this is where the presence of the additives played the major role. Not much in the coalescence, in the collision frequency, but in the coalescence efficiency. So the presence of chemicals affects the drainage time, which appears in this coalescence efficiency. So the drainage time is the time required for the film of fluid in between the two colliding bubbles or drops to break down in order to allow the two bubbles or droplets to coalesce. And this drainage time can be calculated with models coming from physical chemistry considerations. The main governing equation there is the Taylor equation. And of course, bubble size plays a big role, and contact changes the mobility of the interface by accounting for the presence of additives through this drainage time. You can account for the presence of these chemicals. Results that you can get, these are simulations that we run with OpenFOAM by using our own implementation of QMOM and CQMOM for a purer water system. This is a quite old work. These are snapshots of a bubble column. And in this animation, these are experiments compared with simulations. And in this animation, I'm showing you the mean bubble size. So you see that the bubbles are getting out of the sparger. They break down because of turbulent fluctuations. But as the plume moves around, you also have bubble coalescence. This, of course, has a tremendous impact on mass transfer. This is one of the main reasons why we are running these simulations. So in these simulations and experiments, what we do is to basically start at time zero injecting air. Oxygen is moving from the gas phase to the liquid phase. We measure the oxygen concentration in the liquid, and we compare it with the simulations. So the black line is the prediction of the obtained with the full CFD model. The other lines instead are predictions obtained by assuming that the bubbles are monodispersed, they all have the same size, they all move with the same velocity, and the bubble size is in this case more of a fitting parameter rather than a real physical quantity of the multiphase system. We also looked into chemically reacting systems. This is, for example, these are some simulations that we performed on the test case that was investigated by Hans and this group a few years ago, and they also presented some of these results at this workshop. But for the sake of time, I'm going to move on and talk about another interesting gas-liquid system, which is the one referring to boiling flow. This is work done in collaboration with MIT and this research center in Germany. Now, we are not really simulating a real boiling flow. That's too complex for us. So what we do is to simulate a gas-liquid system that mimics what happens in a real boiling flow. So we basically have a pipe, we throw water into the pipe, and then we inject gas bubbles at the wall. This is a cold experiment, room temperature, ambient pressure, and the bubbles are air bubbles. So we run CFD simulations with the entire setup, a population balance plus this distribution, coalescence and breakage, and interfacial forces. And I want you to look at these two plots. This is the gas fraction along the radial direction at two axial positions in the pipe. And here you have the wall, and here inside you have the center of the pipe. As you can see, so these are the experiments. The yellow line and the green line, which are the predictions obtained by using only drag and lift as interfacial forces, are completely wrong because bubbles stick to the wall and do not move from the wall. So to get decent predictions, you need to add additional forces, turbulent dispersion forces, and wall lubrication forces, and this leads you to better predictions. Now, the problem is that there are a number of models available to evaluate all these interfacial forces, and if you combine these models in different ways, they can all lead to very nice agreement with experiments. So again, this is the volume fraction at different axial positions, again, radial gas distribution in the pipe, and as you can see, some of them do agree with experiments. So this way of comparing predictions at these macro scale level with experiments is useful, of course, because it tells you what kind of information you need to plug into the model to get the proper prediction, but it's not going to tell you which one of these models is the least wrong, if not, if you don't want to call it the correct one. And so we are now desperately, I have to confess, trying to make sense of this data, playing especially with the lift force coefficient and trying to understand what could be a way to have something reasonable out of this. All right, so liquid-liquid dispersions. What we do here is mainly look at emulsions and dispersions in stirrer tanks. What we did in this work was to basically take water as continuous phase and we looked at different dispersed phases ranging from pure toluene to silicone oils at different viscosities. And we tried to test different kernels, different models for coalescence and breakage, and see if we could, by using one single set of parameters, fit a large set of experimental data. About 15, if I remember well. So this is, for example, one of the outcomes by using these Colaluglo and Tavlarides kernels, which are extremely simple but very popular kernels to describe coalescence and breakage. This is the mean droplet diameter versus time, experiments versus simulations. And this was, for 2 test cases out of these 15, the best we could get. So by using one single set of parameters, you cannot fit all the data. So of course there is work to do also in this area. We need to come up with better models for coalescence and breakage. And for example, one thing that we are doing is to look into the effect of intermittency. So we are sort of moving away from the homogeneous turbulence theory by Kolmogorov, and we are looking into, for example, the multifractal theory of turbulence to come up with more robust kernels with less empirical parameters, but with parameters that can be also estimated in other ways. And this is just an example. The agreement is better not only in terms of the final steady state value, but also in terms of the dynamics. A very well-known problem is that with Colaluglo and Tavlarides kernels, you get to the steady state too quickly with respect to experiments. Another important issue, which I discussed already, is the presence of additives. As I mentioned, and as a chemical engineer, I'm interested in simulating real systems with real chemicals, so you have many components. These are simulations and experiments run in an emulsion with water and toluene with a surfactant. And as I mentioned before, the way, the place where presence of the chemicals shows up is the efficiency. So this is the efficiency versus the droplet size. And these two lines correspond to different surfactant concentrations. And of course, this is a way to account for that. But one problem you have is that in this drainage time that I briefly talked about before, there are a number of parameters that appear. One of them was also mentioned by Olivier, I think, on Monday or Tuesday, is the critical film thickness, is the thickness of the film shortly before rupture and coalescence. So this is something that is difficult to estimate. This is something that is difficult to measure, and this is an important parameter in the model. So there is, again, work to do in this area, maybe by looking also at atomistic and molecular simulations. And looking at that, especially in liquid-liquid dispersions, is extremely important if you want to describe some hysteresis effects that people see in the experiments. So I don't have time to explain all that, but basically what you do in the stirrer tanks is to play with the stirring rate, going up and down, and you see some hysteresis effects. And if you want to reproduce them with these CFD simulations, you have to account properly for the presence of additives in these in the coalescence efficiency. All right, so these are my conclusions. I'm not going to repeat. I think it was pretty clear there is a lot of work to do, especially for the physical models, for drag coalescence and breakage, as well as the other interfacial forces that I mentioned. One thing I want to mention as final remark is that, and someone else, I think it was Lachlan, it was mentioning that there is a growing effort, especially in Europe, in the idea of building open simulation platforms that can promote the use of CFD, and not only CFD, to a wider audience. So there is a European project that just started, which is called VIMP, which does that or wants to do that in the context of a marketplace for mathematical models. And the platform that we are trying to use for the project is the Salome platform developed by EDF. And we are also planning to integrate some machine learning tools, mainly for parameter fitting and model sensitivity analysis, together with IBM. And then we have a number of industrial partners who are providing us with challenging problem, and hopefully in the next workshop I'll be presenting some results concerning the simulation of a more interesting emulsion, which is mayonnaise. All right, with that I thank you for your attention, and I'll be happy to answer it.
Very nice presentation. I have a quick question, and this is something I spent some time, but